right, in this video I'm going to do some examples of improper integrals. And I'm going to show you, it's not really a shortcut, but it's the cleanest way to write out the process formally. First step, whenever we have an improper integral, we recognize that fact by converting it into a limit. So I'm going to take the limit as b approaches infinity of the integral from 5 to b of e to the negative x dx. Now things are going to get messy unless I solve the antiderivative on its own off to the side. So I'm going to do that. Integral of e to the negative x dx. I'm going to integrate that function. Whatever I get, I'll call it capital F. Now to integrate this, we use substitution. I'll let w equal negative x. dw by dx is then negative 1, and that means dx is negative dw. So we substitute that in, and we get integral of e to the w, negative dw. So negative integral of e to the w, which is negative e to the w plus c, and then we hide the plus c because we have bounds of integration. And the other thing I'm going to do is I'm going to go back to writing the integral in terms of x. So negative e to the negative x. So that's my function. So now this becomes the limit as b approaches infinity of capital F of x, the antiderivative, evaluated from 5 to b. This is the cleanest way to write it. You can do the substitution and change the bounds as well if you want, but it's a little bit more writing. It's a little bit more confusing too. This is the cleanest way. Okay, so limit as b approaches infinity of negative e to the negative x, evaluated from 5 to b. So we have limit as b approaches minus infinity, or positive infinity rather, b approaches infinity of negative e to the negative b, plug in the top bound, and then minus limit b approaches infinity of minus e to the minus 5. So the first part becomes 0. The reason for that is we have e to the minus infinity. E to the minus infinity is 1 over e to the infinity, which is like a 0. Minus e to the minus infinity is equal to minus 1 over e to the infinity, which is minus 1 over infinity, which is 0. And then the second part, minus minus plus, the limit of a constant is just a constant. The second term, negative e to the negative 5, does not contain any b. So it's just like evaluating a constant. The constant doesn't change. So it's just e to the negative 5. So our final answer is e to the minus 5. Okay, next example is a bit neater. I'm going to write this as a limit as b approaches infinity of the integral from 5 to b of e to the x dx. This time we don't need a substitution. I can just take the antiderivative. Antiderivative of e to the x is e to the x. We're going to evaluate this from 5 to b. So limit b approaches infinity of e to the b minus limit b approaches infinity of e to the power 5. So we're going to have infinity for the first part minus e to the 5, which is infinity. The reason we got infinity for this first piece is this is e to the infinity, which is e times e forever. So it's going to be infinity. And subtracting e to the power 5 from infinity does not make it any smaller. Now, I have to attach some language to each of these answers. The first answer, I'm going to attach some language. I'm going to say converges to, and diverges. So the first one, the answer converges to e to the negative 5, and the second one, the integral diverges. Just a fancy word that we attach whenever we get a plus or minus infinity out of the answer. Okay, another example. I'm going to do the first very formal step. This time the lower bound is minus infinity, so I'm going to take a limit as a approaches minus infinity of the integral from a to 3 of e to the x dx. We don't need a substitution. Antiderivative of e to the x is just e to the x, and we're going to evaluate that from a to 3. So we'll have the limit as a approaches minus infinity of e to the 3 minus the limit as a approaches infinity of e to the a, or minus infinity to the a. Little note, I mentioned it, but I want to write it down. Note the limit as a approaches something, the limit of a constant is equal to, well, how do I write this? The limit as x approaches a of a constant. The limit as x approaches a of k is equal to k if k is a constant. So limits do not change constants. For the same reason that function evaluations do not change constants. If f of x is equal to 7, then f of 2 is still 7. The instruction to evaluate a particular x value means replace all the x's with that number. The limit instruction is similar. Take the limit as all the x values approach that number. If there are no x values, then there's nothing to do. In the case we have here, there's no a values in e to the power of 3, so there's nothing to do there. It's just e to the power of 3. And the second part, we have a 0. And the reason for that is that this is e to the negative infinity, which is 1 over e to the positive infinity, which is 1 over infinity, which is 0. But this should not be written. Just some people like having an intermediate step, and you know what? I'm one of them. I like having a middle step, even if this isn't formal mathematics, even if this is like playing with fire, not writing things properly, not writing things formally. This still is somewhat satisfying to me, just personally. I like having some justification for why that's 0, not just quote, hey, it's 0 because the graph. All right. Now we're going from 2 to infinity of the function 3 over x. And this problem is going to require an additional piece of information to solve. Okay, first step, I'm going to recognize this is an improper integral. I'm going to rewrite it as a limit of the integral from 2 to b as b goes to infinity. And then we can take the antiderivative. Antiderivative of 3 over x is 3 times ln absolute value of x, and we're evaluating this from 2 to b. So the limit as b approaches infinity of 3 ln b. I'm dropping the absolute values because b is approaching positive infinity, and the absolute value of a positive number is just that number, minus limit b approaches infinity of 3 times ln of 2. So this last part is just 3 ln 2. What's the first part? What happens when we plug infinity into a log function? Well, it turns out that we get infinity, and I'll explain why. explain why the limit as x approaches infinity of the ln of x is equal to infinity. There's two ways to understand it. One of them is with a graph of a log function. Y versus x. Your log function, no matter what the base is, as long as the base is larger than 1, I guess, the log function has this shape. And if you put a math car on that graph and push the math car towards infinity, the y value will keep increasing and increasing forever. It increases very slowly, but it does increase forever. Second reason is let y equal the limit as x approaches infinity of ln of x. So I'm just going to give it a name, or maybe I'll call it L. Let L equal that limit. I don't know what it is, so what I'm going to do is I'm going to exponentiate both sides. I'm going to say e to the L is equal to e to the limit as x approaches infinity of the ln of x. And I'm going to do something that's a little bit dangerous sometimes. I'm going to bring the limit outside of the exponential. Limit as x approaches infinity of e to the ln of x. So e to the L equals, in the cancellation law, limit as x approaches infinity of just x. So this is equal to infinity. And then e to the L is equal to infinity means L is equal to infinity. There's no other possibility. So either know what the graph looks like, or memorize that the ln of infinity is infinity, or understand algebraically that you can get this result by thinking about e to what power gives you infinity, thinking about that graph, or thinking about the algebra. E to the power of 200 is not infinity. It's some big number, but it ain't infinity. The only way you're going to get infinity out is if L is actually equal to infinity. Anyways, jumping back to this, we have infinity minus something that's small. We just get infinity, and that's our answer. It diverges. Diverges to infinity. Now think about what this is calculating. This is calculating an area under a curve from 2 to infinity. This is important. An area under y equals ln of x, or y equals 3 over x, from x equals 2 to x equals infinity. So it's saying that this area of the function 1 over x from 2 onward, right, keeps going forever. We keep shading in and it never stops, keeps going to the right, saying that's an infinite area, which you may say, well, of course, if it never stops, right, you keep painting and painting. Like imagine painting that surface, getting on a paintbrush and just painting as you move to the right. Well, of course it has to be infinite, right? Like, because you're going on forever. So keep that thought in mind when we go to the next example. I want to find the area under this region, the region under 3 over x to the power 4, for x greater than or equal to 2. So the x value keeps increasing forever. I want to know how much area is there. So it never stops. Region has an infinite width. Does that mean the area is infinite? Because whatever that shape is, you might be able to imagine putting a little rectangle in the bottom and saying, well, the area rectangle is length times width, and if the width is infinity and the length is anything, then the area is going to be infinity. Let's do the calculation and see what happens. Let's see if our intuition is right, that this is going to be infinity too. Infinity as well. Okay, so the area is equal to the integral from a to b of the top function minus the bottom function. Now a, we're going from 2. B, we're going up to infinity. The top function is 3 over x to the power 4. The bottom function is 0. We're using the x-axis as our bottom. I'm going to rewrite this as the integral from 2 to infinity of 3x to the power of negative 4 in preparation for using the anti-power rule. And I'm also going to be formal about this, take the limit as b approaches infinity, integral from 2 to b of 3x to the power of negative 4. Let's see what happens. Antiderivative of 3x to the power of negative 4, we're going to have 3 times 1 over negative 3, x to the power of negative 3. The power goes up by 1, and we divide by the new power. And this is evaluated from 2 to b. So it's negative limit b approaches infinity of 1 over b to the 3 minus negative limit b approaches infinity of 1 over 2 to the power of 3. This first limit is 0 because we have 1 over something huge, 1 over infinity to the power of 3. Second limit, negative negative plus, becomes 1 over 8. So we get an overall answer of 1 over 8. That's not 0. Oh, so that's not infinity. It converges. The area is not infinite, despite being infinitely wide. This should bother you immensely that this has happened. The previous example was a very similar type of function, 3 over x, compared to 3 over x to the power 4. They both have the same type of decay shape. They both approach 0 as x goes to infinity, but they never touch 0. This first example, the 3 over x, the yellow region I have in the bottom there shaded in, that is an infinitely large area. The calculation tells us the area is infinity. This shape is similar. It goes to 0 more quickly, and the calculation tells us that the area is not infinite. It's finite. It's 1 over 8, 0.125. And I'm not sure what to say about that, because we didn't talk about sequences in series. We don't have that in the course. We don't have infinite sums explicitly mentioned. So you'll have to leave this as a mystery as to why this is happening. Why is it that we're adding up this seemingly infinitely large area and getting a finite answer? It requires, I think, to understand or to fully appreciate how significant this type of result is, we would need to talk about some other topics. Some topics called sequences in series. Not part of the course. So why is it, I just want to talk about that limit again. Limit as b approaches infinity of 1 over b to the power of 3 goes to 1 over infinity to the 3, which is like 1 over infinity, which is 0. But don't write that. We're not really supposed to show any middle steps. Okay, another example. We want to find 12 times this integral. So we have 12 times the limit as b approaches infinity, integral from 0 to b of x to the power negative 3 over 2 dx. Antiderivative of x to the power of negative 3 over 2, the power increases by 1. So negative 3 over 2 plus 1 is negative 1 over 2. So x power negative 1/2. And the number in front, we would do 1 over that, 1 over negative 1/2. This is evaluated from 0 to b. Oh, it can't be 0. I'm a bad person. Let's change the question. Please change the question to a 1, not a 0. I don't want to have that other problem here. So 1 to infinity. I want this to be like the other ones. Don't involve anything else weird. All right, so use the anti-power rule, take the antiderivative. Dividing by 1/2 is the same as multiplying by 2. So we're going to have a negative 24. And then limit b approaches infinity of 1 over the square root of x, evaluated from 1 to b. So a negative 24 times limit b approaches infinity of 1 over the square root of b minus negative 24 times limit b approaches infinity of 1 over the square root of 1. So we get negative 24 times 0 plus 24 times 1. So we get 24 as our answer. And I'll explain where the 0 came from. So limit as b approaches infinity of 1 over the square root of b, it goes to 1 over the square root of infinity. Well, what number can you multiply by itself to give you infinity? Well, that's what square root means. Square root of 4 means what do you multiply by itself to give you 4? Well, let's say, can you multiply 50 trillion by itself to get infinity? No, it's too small. The only thing you can multiply by itself to get infinity is infinity. And 1 over infinity, you think about that lottery, 0 odds of winning. So that's why it's 0 there. And I should attach the keyword, special word, it converges to 24. Okay, next example. And I have to change that lower bound once again. I'm going to change it from 0 to 1. My apologies for not catching that. You won't even see that when you download the note. It'll be fixed. Integral from 1 to infinity, 12x to the power of negative 1/3. So I'm going to do the same thing as before. I'm going to be very formal. Take the limit as a approaches. Oh, not a, it's b. It's the top. B approaches infinity. Integral from 1 to b. And I'll put the 12 out front too. 12. And then x to the power of negative 1/3. And we'll use the anti-power rule. So the antiderivative of x to the power of negative 1/3, the power increases by 1, so negative 1/3 plus 1 becomes positive 2/3. So x to the positive 2/3. And we have 1 over the new power. Remember 2/3 in front, evaluated from 1 to b. And then that's going to be 12 multiplied by 3 over 2. Times limit as b approaches infinity of x to the 2/3 from 1 to b. So 18 limit b approaches infinity of b to the 2/3 minus 18 limit b approaches infinity of 1 to the 2/3. And this is going to be 18 multiplied by infinity. And here's why. and y in a second. So this diverges. We get 18 times infinity minus 18, which is infinity. So limit as b approaches infinity of b to the power of 2/3. This turns into infinity to the power of 2/3, which is the cube root of infinity all squared. What number do you multiply by itself 3 times to give you infinity? Well, the answer is infinity. What's infinity squared? Infinity. That's y. But don't write this. It's not proper mathematics. Okay, another example. So I have limit b approaches infinity. I'm just going to right away acknowledge that this is a improper integral. Then I'm going to think about the strategy that is needed to solve this. How to take the antiderivative of 4x e to the negative x squared. We need substitution. So whenever there's an improper integral with substitution, I highly recommend using the other method for working with definite integrals. Find the general antiderivative, capital F of x, and then whatever it is, you're going to get capital F of x evaluated on the bounds. And we have to find what that capital F of x is. So capital F of x is the integral of 4x e to the negative x squared dx. Substitution, w is equal to negative x squared. I use that because that's the part that's being plugged into a component of the expression. So that's going to be, when we take the derivative dw by dx, we'll get negative 2x. And then cross multiply and cross divide, we get dx is equal to negative dw over 2x. I'll plug that in for the dx there. This becomes 4x e to the w multiplied by negative dw over 2x. There's an x on top that cancels with the x on the bottom. We've eliminated the old variable completely, which means our substitution was successful. We still have a 2 in front. 4 over 2 doesn't completely cancel. That's okay. And it's a negative 2. We're going to bring the negative sign with it, times the integral of e to the w. So this is negative 2 e to the power of w plus c. We can ignore the c because of the bounds. And I'm going to undo the substitution. I'm going to replace the w with negative x squared. Negative 2 e to the negative x squared. And I'm going to plug that in over here for capital F of x. So we have the limit as b approaches infinity of negative 2 e to the negative x squared evaluated from 0 to b. So that'll be negative 2 times the limit as b approaches infinity of e to the negative x squared minus negative 2 limit b approaches infinity of e to the 0. We'll get negative 2 times 0 plus 2 times 1. I'll explain where the 0 came from. Limit as b approaches infinity of e to the negative x, forgot to replace the b, oops. This would be at b squared of negative b squared. That's going to be e to the negative just infinity squared. The negative sign is not part of what's being squared. Just the b part is being squared. Infinity squared is infinity, so I have e to the minus infinity, which is 1 over e to the infinity, which is 1 over infinity, which is 0. Okay, and then we can say that it's equal to 2. And more formally, we would say it converges to 2. We could draw a picture of this graph, the graph of 4x e to the negative x squared, and the area is infinitely wide for what's shaded underneath that graph, but the area is still finite. So infinite width, but the total area is not infinity anyway, because that function, 4x e to the negative x squared, decays, falls to a y value that's very small, very quickly. All right, let's combine our knowledge with our knowledge of improper integrals with our knowledge of absolute value functions. So you see an absolute value function, we have to treat it as a piecewise. It's equal to negative x for x less than 0. It's equal to positive x for x greater than or equal to 0. So this becomes the integral from minus infinity to 0 of e to the 3 minus negative x. So that's for the left-hand side of the number line. For x less than 0, absolute value of x gets replaced by negative x. And then my second half of the integral from 0 to infinity of e to the 3 minus positive x. Then we can simplify. This becomes integral from minus infinity to 0 of e to the 3 plus x plus integral from 0 to infinity of e to the 3 minus x. Now this is going to be interesting here. We're going to do two different antiderivatives. The first one will have a limit as b approaches minus infinity of capital F of x evaluated from b to 0 plus limit as a approaches infinity evaluated from I guess this is A, the first one, just to be consistent with how I was writing it before, from 0 to b. And I'm going to use colors. I'm going to say this first one is capital F of x in black, and the second one is capital F of x in red. Oh, and this should be a B, not an A. So I rewrote both of these using the proper format for improper integrals, taking limit wherever there's an infinity and or a minus infinity. So I have to calculate those antiderivatives now. I'll do that off to the side. Capital F of x is the antiderivative of e to the 3 plus x. And if you go through the substitution, w is equal to 3 plus x, you'll get dw is equal to dx. So your integral transforms into the integral of e to the w tw, which is e to the w plus c, which is e to the 3 plus x plus c. So that'll go here. And we can drop the plus c. Okay, so that's the first part. Evaluated from a to 0. Now the second part, limit as b approaches positive infinity. We have to calculate that from b. So what's that function going to be? Capital F of x is the integral of e to the 3 minus x. We'll do the same type of substitution and let w equal 3 minus x. This time we find dw, or dx is equal to negative dw after rearranging, after taking the derivative. So this turns into negative integral e to the w dw, so negative e to the w plus c, which is negative e to the 3 minus x plus c. Oh, no plus c. We can ignore the plus c once again. Okay, so that's going to be what I put there. Negative e to the 3 minus x evaluated from 0 to b. Okay, plugging in the bounds now. Limit a approaches minus infinity of e to the 3 minus limit a approaches minus infinity of e to the 3 plus x. And for the second part, we'll have plus limit e approaches infinity of negative e to the 3 minus b plus, or not plus, minus limit b approaches infinity of minus e to the 3, replacing x with 0. And we can clean this up. Limit of a constant is just a constant, so we get e to the 3 there. Second part, we get 0. Third part, we get 0. And the last part, we get e to the 3. And we can conclude by saying that the answer converges to 2e to the 3. The reason why those two limits are 0 is they're both of the form e to the negative infinity. So 3 minus infinity is negative infinity. E to the minus infinity is 1 over e to the positive infinity, which is 1 over infinity, which is 0. So the same reasoning as all the other ones. Okay, here's a similar example. So the difference is, inside the one we just did, it's 3 minus x. In this example, it's negative 7 multiplied by x. So I'm going to split this up since this is a piecewise function. Negative x or positive x, depending on what x value we have. This allows us to split the integral at 0. Negative 7 times negative x for the first region. And for the second region, from 0 to infinity, x, or absolute value of x gets replaced by positive x, so we get e to the negative 7 times positive x. And then we can simplify. We can write the first one as the limit as a approaches minus infinity of the integral from a to 0 of e to the positive 7x. And the second one, limit as b approaches infinity of the integral from 0 to b of e to the negative 7x. Each of these will require substitution, so I'm going to say that this is going to be the general antiderivative capital F of x evaluated from a to 0. I will take a limit of that, plus the limit as b approaches infinity of the general antiderivative. I'll use a different color, capital F of x evaluated from 0 to b. And then I'll calculate those off to the side. So the first one, integral of e to the 7x. We let w equal 7x. And then do all that rearranging stuff. And we'll find we get 1 over 7 integral of e to the w dw. So 1 over 7 e to the 7x. I guess I'll do it in two steps. E to the w plus c. and then we can hide the plus c, replace the w with 7x. Okay, and that's going to be what we substitute there. And for the second piece, capital F of x this time is the integral of e to the negative 7x. And we'll use the same type of substitution. W is negative 7 times x. Do the dot 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 stuff, all the dw, rearrange, and our integral becomes minus 1 over 7, integral of e to the w, dw. So minus 1 over 7 e to the w plus c. And then replace the w with what it was originally, negative 7x. Hide the plus c due to the bounds of integration. Okay, that's what we put in the second spot. Minus 1 over 7 e to the negative 7x. Okay, then we're going to take the limit and evaluate. So for the top bound, we get 1 over 7 e to the 0. For the bottom bound, we get 1 over 7 e to the negative infinity, which is 0. And then for the second part, I plug in the top bound, we get minus 1 over 7 times 0. For the same reason, they're both e to the negative infinity, which is 0. And we get minus 1 over 7 e to the 0. And we can simplify 1 over 7 times 1 plus 0 plus 0 plus 1 over 7 times 1. And we get 2 over 7 as the answer. So this one also converges. Okay, and then some tougher examples, some test style examples, and I'll pause the video here.